We are continuing to work sample problems for section 11.4 on binomial probabilities, and I want to do one more example. And this one, actually maybe I'll do a couple of examples just to get us going with this. We're still making use of the formula, the binomial probability formula, where we're talking about the probability of x successes and n trials. We take combinations of n taken x at a time times the probability of success raised to the x power and times the probability of failure raised to the n minus x power. So I'm going to work on numbers 40 through 43. These all deal with the same case. So let me read you the scenario. In a certain state, it has been shown that only 60% of high school graduates who are capable of college work actually enroll in college. Find the probability that among 9 capable high school graduates in this state, each number will enroll in college. So we have a probability of success, that's enrolling in college. That means the probability of failure would be 1 minus 0.6 or 0.4. We're talking about 9 students. So our n is 9. And so in number 40, they want the probability that exactly 4 of the 9 enroll in college. So we're going to use probability of 4, probability of 4, x is 4, is combinations of the 9 taken 4 at a time, times 0.6 to the 4, times 0.4 to the 9 minus 4 would be a 5. So let's see. We want to find the combinations of 9 taken. Got to start over. Combinations of 9 taken 4 at a time. That's 126. So 126 times 0.6 raised to the 4th times 0.4 raised to the 5th. And I'm coming out with 0.1672, etc. So I'll just drop off the remaining digits. Okay, now here's where it gets to be a little bit different from what we've done before. From 4 through 6. So in this case, we're going to have to calculate for 4, which we've already done, for 5, and for 6, and then add them all up. So for 5, so 9 minus 5 would be 4 there. So we're taking 9 combinations, taking 5 at a time, and we get the 126 again. So that will be 126 times 0.6 raised to the 5th times 0.4 raised to the 4th. So I'm getting 0.2508, so I'll have to round that to a 1. Okay, and whoops, that's for 5. Okay, for 6, and I may have trouble squeezing this in here, we want combinations of 9 taken 6 at a time. 0.6 to the 6 times 0.4 to the 9 minus 6 would be 3. Alright, so if I do combinations of 9 taken 6 at a time, whoops, I get 84, and I want to take 84 times 0.6 raised to the 6 times 0.4 raised to the third, and I'm getting 0.251. So now to get the answer for this, I need to add 0.167 plus 0.251 plus put the 0 in there. It helps us to see the decimal point. So this is for 4, this is the probability for 5, and this is the probability for 6. So I'm going to add these up. And I'm getting 0.669. So in some cases you may have to add up your answers, so be aware of that. And let's do 43. I don't think we need to do. In 43, it says at least 3. At least 3. So what are we going to have to do? We may not actually do it. Probability of at least 3 means 3, 4, 5, 6, 7, 8, 9. So we have to calculate all of these probabilities and add them together. The other alternative, because of the complements rule, we could take 1 minus the sum of the probabilities for 0, 1, and 2. And as I'm looking at that, that to me would be the way to go, simply because, let me put square brackets around that, simply because we'd only have to calculate 3 probabilities, add them together, and then subtract that from 1. So we could use the complements rule. So you do have the option, though. You can do it the longer way if you're more comfortable with that. I would go with the complements rule simply because it would be quicker. And let's see if we can do this one on the next page. If we do probability of 0, probability of 1, probability of 2. So we want to do probability of at least 3, and we're going to take 1 minus the sum of those 3. We're going to use complements. So that's our way of thinking. And in this case we had n was 9, x's are 0, 1, and 2. Probability of success was 0.6, and probability of failure was 0.4. So this is going to be combinations of 9 taken 0 at a time, 0.6 raised to the 0 times 0.4 raised to the 9. 9 taken 1 at a time, 0.6 raised to 1, 0.4 raised to the 8. And finally, combinations of 9 taken 2 at a time, 0.6 squared times 0.4 to the 7th. So let's calculate these. I believe we're going to get a 1 for the first one. Okay, so 0.6 to the 0 is also 1, so 0.4 raised to the 9th will be our answer. Okay, and I'm getting 2.62 times 10 to the negative 4 So 1, 2, 3, 4. Okay, I'm just going to go ahead and write it in its decimal format. And the next one, I think, combinations of 9 taken one at a time would be 9 times 0.6 times 0.4 raised to the 8th. It's going to give us 0, 0, 3, 5, 4 if I round it off. And I am rounding here, which is not always the best thing to do, but anyway. Combinations of 9 taken 2 at a time. I get 36 times 0.6 squared times 0.4 raised to the 7th. And I'm getting 0.02123. So I want to add these together. And I'm getting, if I didn't make any errors, 0.025031. So minus 0.025031. So I want to take 1 minus that. And I'm getting 0.975 if I round it to the nearest thousandth. Okay, and that's the correct answer. So again, on this one, you could, if you want it for at least 3, you could add up the probability 3, 4, 5, 6, 7, 8, and 9 successes. I chose to do the complement because it's a lot shorter. So for the complement, we choose everything that's not at least 3. That would be 0, 1, and 2. And then we subtract the sum of those probabilities from 1.